My wife and I enjoy playing the board game Sequence. Why? Well, because it's pretty mindless. You just draw a card, put a chip on the board, and you try to get 5 chips in a row. You basically try to build a sequence. And when we think about a sequence, we're really just talking about something that's in some type of order, like the numbers 2, 4, 6, 8, and 10. Now, when you look at those numbers, you should say, well, Ms. Naylor, those are really just even numbers. In fact, it's the first 5 even numbers. And sure, they're a sequence. They're in an order. What if I asked you for the next number? Well, pretty easy, right? You'd say 12. How about the nth number? What do you mean the nth number? Well, the nth number would be any term in the sequence. Maybe the 50th term or the 100th term. Well, to do that, it would be nice to have a formula, wouldn't it? And when you think of a formula, you want to think about how you can describe any number or the nth term. Well, look, each one of these terms is in a multiple of 2. It would make sense to consider multiplying by 2. How about 2 times n? Now, n represents the term. So if it's the 5th term, I would plug a 5 in for n. Now, of course, you would get 2 times 5, which is 10. Looks like that's the 5th term. So could I now get the 50th term? Sure, just plug in 50 for n, and you get 100. How about this sequence? Well, it's in an order too, isn't it? It's the first 5 odd numbers. Do you think you could write a formula for the nth term? It would be kind of silly to say 3n, wouldn't it? If you think about it, 3n would say that, well, that the 5th term would actually be 15. But the 5th term looks like it's 11. So we have to get a little more creative with our formula. We could write it as maybe 2n plus 1. If you add 1 to every one of those original even numbers, you'll be at now these odd numbers. And so 2n plus 1 is a formula for the nth term. In other words, any term in this sequence. Try it. If I want the 50th term, I can plug 50 in for n. And of course, I'll get 2 times 50, which is 100, plus 1. So it looks like the 50th term would be 101. How about this sequence? 1, 2, 6, 24, 120. Let's try that again. 1, 2, 6, 24, 120. Why would I be shouting these numbers? Well, to get you to realize that this sequence is a factorial. Yes, a factorial when you use an exclamation mark to describe a number. Now, 1 factorial would just be 1 times 1. 2 factorial would be 2 times 1. But 3 factorial, well, that would be 3 times 2 times 1. And that gives you 6, doesn't it? How about 4 factorial? Remember how factorials work? 4 times 3 times 2 times 1. What you do is you multiply the number times each integer all the way down to 1. And I hope you double check that this one comes out to be 24. And then the last one in the sequence is 5 factorial, which is just 5 times 4 times 3 times 2 times 1, which is 120. So could you write this one? Could you write a formula for the nth term? Yeah, it's just going to be n factorial. We have a lot of different sequences, a lot of different ways to put numbers in some type of order with some type of pattern. So speaking of patterns, how did you do with the little cube preview where you were trying to do some counting but then ultimately tried to describe the pattern using a formula? Kind of interesting. Here's your answers. Just as a little bit of a highlight, the one shaded face sometimes catches kids' attention. One shaded face. That's always going to be these cubes that are sticking out, but only sticking out in the middle of each side. And so, for example, I'm just kind of highlighting the 4 shaded faces that you see on each side. That's why for 4 by 4 we end up with 24. Has to do with writing some formulas. You may have noticed for 2 shaded faces that we went from 12 to 24 to 36. A lot of students realize that we're like going up by 12s, but how do you describe that? Definitely by multiplying by 12, as you can see here. But we always want to be 2 less than the number of n that we use. So n minus 2 times 12. Okay, now I did look at one of these for correctness, but ultimately I wanted you to try the activity. If you're curious which one I looked at, it was n minus 2 to the power of 3, because each of these numbers was a perfect cube, but we had to subtract 2 again to kind of bring our base number down so that it would match with the, in this case, 0 shaded faces. Well, every problem that we've done so far has been in some type of order or pattern, and it's going to be our Unit 6 that we're going to begin today on sequences and series. And that's exactly what a sequence is. It is just numbers that are in some type of order, and again, can always be described with a formula that will give that particular pattern or order. Now, a series is the sum of the terms in a sequence. And I like to always show kids that definitely a series is a different idea because it's technically going to come out to be an actual sum. It's going to come out to be an actual number. And so if you just take my first even numbers that I showed a few slides ago and you decide to turn that into a series, well, then you'd have to add all the numbers together. And it looks like we would come up with what here? I believe the number 30. So a sequence is actually the order of numbers, but a series comes out to actually be the sum of those numbers. Well, today, for our first topic, we're going to look specifically at an arithmetic sequence. Now, first of all, you want to pronounce that right. It's not arithmetic, it's arithmetic. And an arithmetic sequence is when your terms have a difference that can be described as being constant. In other words, you'll argue or you'll realize that your terms are always some equal number apart by addition. And we would say then that the difference, again, between the terms is constant. So let's look at some arithmetic sequences. Let's dig a little bit deeper to see the numbers 2, 7, 12, and 17. It's pretty easy to determine the next term. Geez, I could ask you for the next 3 terms, and I know you could list them. You know, let's at least list the next term here. I hope you would say 22. But really, what I want you to realize is that that number 5 that you were coming up with, well, that was called the common difference that we were referring to on the previous slide. And the common difference is always the constant value that you are that is changing by. And we actually usually just we just kind of make it simple by calling that d. How about these numbers? 8 plus 8 pi, then 8 plus 6 pi, and then 8 plus 4 pi. Now again, you could tell me the next number, right? I hope you would say that it's 8 plus 2 pi. But that's because you recognize that each one of these terms is going down by the same common difference. Again, we'll just denote that with a d. Yes, it's going down. And so the common difference would be negative 2 pi. Yes, a common difference can be negative. Now, so far, this isn't too hard, but let me help you to see that we can start to describe each of these terms using some notation. Now, 2 is our first term here. We're going to call that a sub 1, again, to denote the first term. 7 is our next term. We'll call that a sub 2. But I'd like you to notice that we can describe it. Let me go back. We're not going to call it a sub 2. Instead, we're going to describe it using a sub 1 and our common difference. In this case, a sub 1 plus d. How about the next term here? Could I describe this as a sub 1 plus a certain common difference? Well, yeah, if I'm starting at a sub 1, then I use 2 common differences. The next term could be a sub 3. plus, excuse me, not a sub 3. It would still be described with a sub 1, but this time with 3 common differences. Now, what I'm trying to help you to see here is that each term in this sequence can be described with the first term plus a certain amount of common differences, in this case, 4 common differences, which would help us to describe the nth term. Now, the nth term would be basically any term that's in this sequence. And we should notice here that the nth term can always be described using the first term. Let's see if we can squeeze this in here, using the first term plus how many common differences. Not n common differences, okay? Because if you look here, the second term only used 1 common difference. The third term used 2 common differences. So the nth term is going to use n minus 1 common differences. We would say that it's a sub 1 plus n minus 1 times d. What do you think? That's the formula for the nth term of an arithmetic sequence. It's always going to be the first term, a sub 1, plus n minus 1 times d. Now remember, the letter n just stands for the position of your term. So, what if I wanted to find, like, the 50th term of this example? I'm sort of running out of space here a little bit, but to help you see that, I could say that a sub 50, the 50th term, is going to come out to be the first term, which is still 2, plus, well, 50 minus 1, n minus 1, times that common difference of 5. And we got ourselves a pretty easy little equation here where we can just, find out that we have 49 fives, which is 245, plus 2, that first term, we end up with 247. A sub n, the nth term. It's always the first term plus n minus 1 times common difference. Now, this formula allows us to do some more advanced problems. You know, like a problem where maybe I want to find the first term, but I'm all the way down the path at the 91st, 92nd term. Now, listen, I'm not expecting you to go backwards 90 times. Okay, that's not the idea here, but rather I'm asking you to try to use the formula. Now, students that use the formula will realize, first of all, that we need the common difference. It looks like that's 6,254, and then 6,260 would have increased by 6. If, as I continue to solve this, I can plug into my formula. If I choose to, I can plug in the 91st term. That is a sub 91, which is 6254. So I'm plugging in the 91st term. I'm trying to solve for the first term, so we'll leave that as a variable. And then we're going to plug in 91 minus 1, and then times our common difference of 6. Listen, why did I plug in the 91st term? Because that's what I was given. Could I have plugged in the 92nd term? Yeah. Then I would have used a 92 in my formula. But the bottom line here is I'm plugging into the formula, and I'm going to be able to solve this for a sub 1. Solve it carefully. This comes out to be 546 when you multiply by 6. And so basically I'm going to go backwards by 546 units back to 5,714, I believe, to be my first term. It's a pretty nice formula. We want you to get comfortable using it. It can help with some other type sequence questions. Here's one where we're trying to find some missing numbers. Now, I like to say that there's 2 ways to do this. You could do it with brute force. Brute force would be that you start kind of guessing numbers between -11 and 19. Another sort of brute force method would be that you do a little bit of maybe some addition or subtraction. I've seen students that sort of try to do this problem on their own. They'll essentially try to find the difference between these numbers. Now, the difference between these numbers would be subtracting them. It comes out to be 30. But then what? Are you going to divide by 5? Are you going to divide by 6? Both of them seem to divide evenly. My point here is that you want to use the formula. And when you use the formula, you'll realize that it will help you to find the common difference. That's really what we don't know here, right? We don't know the common difference. So let's see if we can do a little plugging in. How about we call this a sub 1, 3, 4, 5, 6, and then we'll call this a sub 7. There's no reason I can't say that. It's like the first term and the seventh term. The nice thing about that is it allows me to start plugging into the formula. I can plug in 19 for a sub n. In other words, kind of like one of the numbers down the road. Obviously, negative 11 gets plugged in for a sub 1. Now, do you realize that I've decided that n equals 7? That's because I plugged in the seventh number. So I can plug 7 in for n. And lo and behold, it gives me a formula that I can solve for d. Now, check this out, especially my brute force kids, because if you start solving this equation, you find out that that you get some of the same numbers that we already found. Namely, we get the number 30, and then we find out, oh, okay, I should divide by 6. Yeah, you're actually equally dividing 30 by 6, and that gives you confidence that the common difference is 5. And then I would expect you just to add 5 to each of these. Nothing too tricky. Of course, just add carefully. And if you keep adding 5 carefully, you'll get yourself up to 19. Arithmetic formula. Okay, pretty nice, especially when we're working with arithmetic sequences. So what if we want to do an arithmetic series? Remember, a series is just the sum of the numbers. So if I have some numbers like a sub 1, a sub 2, a sub 3, ... a sub n. Again, to make this into a series, all I would have to do is add those numbers. And so I can add a sub 1 plus a sub 2 plus a sub 3, and obviously as many numbers as I need to add down to a sub n. But what if I had like 100 numbers or like 1,000 numbers? Yeah, that would be sort of a pain in the butt to have to add all those numbers together on your calculator. Let's see if we can come up with a formula. Let's see if we can sort of one-up the math here and figure out how to add 100 numbers together. Now, to do that, I'm going to sort of backtrack a little bit here again and say that the series of n numbers, now this is just a little notation, S sub n means the series of n numbers. In other words, adding n numbers together, which would be the same as adding a sub 1 plus, well, instead of writing a sub 2, we're going to write it as a sub 1 plus that common difference. And then, of course, the next term is a sub 1 plus 2 common differences. Remember, every term in an arithmetic sequence can be described with the first term plus so many common differences. Now, I'm running out of space horizontally here, so I'm going to just skip down to the next row. And I want to work backwards with you because what would be my nth term? Well, it would just be a sub n. But what about the term before the nth term? Well, it would be a sub n minus 1 common difference. Well, what about the term before the last term? It would be a sub n minus 2 common differences. Now, this is some notation, and I know this can be a little tricky, but you have to understand here that I'm simply arguing that, well, if you have numbers in order, they're always going to be separated by so many common differences. And up to my last number, which is a sub n, and the number before it and the number before that. Something kind of interesting can start to happen here. You see, math can be romantic. It's in the business of trying to make matches. And I think I see a match. I think I see the first term being able to match up with the last term. You say, what do you mean? Well, just run with this with me here. If you take the first and the last term and you match them together, you have a sub 1 plus a sub n. But what if you take the second term and the second to last term and you match them together? Yeah, do you see what's going to happen? You're going to end up being able to cancel out the d's. Oh, and I end up with another a sub 1 plus a sub n? Yeah. Let's match some more terms. We seem to be doing a good job with some matchmaker. So, those two d's, they're going to cancel out, right? So now I have a sub 1 plus a sub n again. Well, how many of these matches am I going to make? Don't say 3. How many of these matches am I going to make? How many a sub 1s plus a sub n's will I end up listing here? It depends on how many n's, it depends on how many numbers I list in the first place, right? Well, those numbers are n, but it's always going to be half of them. It's always going to be n divided by 2. Wait a minute, what just happened here? Well, we wrote a formula for the series of n numbers. Look at it. It's just the first term plus the last term times the total number of terms divided by 2. This is the formula for an arithmetic series. It's pretty sharp. All I need to do when adding up a whole bunch of numbers is to know the first term, the last term, the total number of terms, that's n, and then just divide that answer by 2. Do you trust me? Do you think it will, that it'll actually work? What if I want to add these first 5 even numbers? We already figured out in one of the previous slides that should come out to be 30. Pretty easy math. But what if we use our formula? Well, the series of these 5 numbers, in other words, the sum of these 5 numbers, is going to be the first term plus the last term times the total number of terms divided by 2. What do we end up with here? We end up with 12 times 5, which is 60, divided by 2. We end up with 30. And where this formula really excels is if I have, a lot of numbers, like what we would typically call a partial sum. If I ask you to add the 27th partial sum, that's just fancy talk for add up the first 27 numbers represented by this sequence, where we go from -2 to -8 to -14. Ooh, wait a minute. Yeah, you're right. I don't want to add 27 numbers together, but I also don't know what the 27th number is. Uh-oh. Wait, the 27th number. Oh, that's going to be the nth number, the arithmetic formula. So if I want to find the 27th number, a sub 27, I just need the first term. Okay, well that's -2. I've got the first term plus the total number of terms, so 27 minus 1. And then we need this d value. Yeah. And if you look at -2 to -6, or check that to -8 to -14, you should have said that d equals -6. So, okay, I've got my little formula, and I can solve for the 27th number. It comes out to be -158. Now, what you want to realize is that's kind of the missing piece to this problem, because now that I know that the 27th number is -158, I can plug into my series formula to find the 27th partial sum, which again is just fancy talk for let's add up these 27 numbers. Well, since I know that it's 27, we can divide that by 2, and then I just need the first term and the last term. Look, 2 things I wanted you to notice from this problem. It works with negative numbers, and it also works if there's an odd number of numbers. Because even though it's 27 divided by 2, which is a decimal, it's still really going to be in this case, -160 times 27, and then you're just going to cut that answer in half. So what do you get? Well, you get kind of this big number here, -2,160. Make sure you realize that -2,160 would be like taking -2 plus -8 plus -14 plus -20. Yeah, I'm not going to do that on my calculator, but if I add up 27 of those numbers, I'm going to get negative 2,160. Call that a series, or the 27th partial sum of that series. Your turn. There's an exit problem. It's a good problem. It's going to make you kind of combine two ideas, a little bit like what I did in the last problem in this lesson. There's actually a form on Classroom. So you're going to submit that through Classroom, and then you'll be ready to take a look at the homework that comes out of the book. All right, we'll see you next time.